You touch it every day and never think twice. The seal around your phone, the soft spatula in your kitchen, the flexible tube in a hospital, the waterproof coating on your outdoor gear. It feels almost magical. Heat-resistant, water-repellent, flexible yet strong, and somehow made from one of the most ordinary materials on Earth, sand. But turning ordinary sand into the high-performance material we call silicone is one of the most elegant chemical journeys ever invented, and the real story is far more surprising. First, a quick distinction that confuses almost everyone. Silicon is an element. It sits just below carbon on the periodic table. It is the second most abundant element in Earth's crust. It makes computer chips. It is hard, crystalline, and brittle. Silicone is something completely different. It is a synthetic polymer, long chains of alternating silicon and oxygen atoms with organic groups attached. It can be liquid, rubbery, or resinous. It is engineered, not mined. So how do we go from beach sand to this remarkable material? It starts with pure silica, silicon dioxide, the main component of quartz sand. In massive electric arc furnaces, silica is mixed with carbon, usually in the form of coal, coke, or wood chips, and heated to temperatures between 1,500 and 2,000 degrees Celsius. At those extreme temperatures, carbon strips the oxygen away from the silicon. What remains is metallurgical-grade silicon metal, a silvery, crystalline solid about 98–99% pure. That silicon is then ground into a fine powder. Next comes the key industrial breakthrough, the Müller-Rochow process, also called the direct process. Independently discovered in the early 1940s by American chemist Eugene Rochow at General Electric and German chemist Richard Müller, this reaction still powers the modern silicone industry. Powdered silicon is heated with methyl chloride gas in the presence of a copper catalyst, typically around 300 degrees Celsius. The reaction produces a mixture of methylchlorosilanes. The most valuable product is dimethyldichlorosilane, the primary building block for the vast majority of silicones. These chlorosilanes are carefully distilled and separated. Then comes the transformation that creates the polymer. Dimethyldichlorosilane is reacted with water in a process called hydrolysis. The chlorine atoms are replaced by hydroxyl groups, forming unstable intermediates that quickly link together. The result is long chains of alternating silicon and oxygen atoms, polydimethylsiloxane or PDMS, the backbone of most silicones. Hydrochloric acid is produced as a byproduct and is often recycled back into the process. By controlling the reaction conditions, chemists can create chains of different lengths. Short chains become silicone oils and fluids. Longer chains become gums that can be turned into rubber. Cross-linked structures become resins. Further steps refine the material. Fillers such as fumed silica are added for strength. Curing agents, peroxides, or platinum catalysts are introduced so the material can be molded and set. Pigments, stabilizers, and specialty additives customize performance for medical, food, automotive, or aerospace use. The final forms are astonishingly versatile. Liquid silicone rubber that can be injection molded into precise medical devices. High-consistency rubber extruded into tubing and seals. Silicone oils that lubricate at extreme temperatures. Resins that protect electronics from moisture and heat. Have you ever wondered why silicone bakeware doesn't stick? Or why a silicone seal survives decades of weather? Or why medical-grade silicone can live inside the human body? It is because the silicon-oxygen backbone is extremely stable. It resists heat, cold, oxidation, and chemical attack far better than most organic polymers. The story of how we learned to make it is equally remarkable. Early chemists in the 19th and early 20th centuries, including Frederick Kipping, created the first organosilicon compounds. Kipping even coined the name silicone. But the materials were hard to produce and seemed useless at the time. Everything changed in the 1940s with the direct process. Suddenly, large-scale production became possible. During World War II, silicones found critical uses in aircraft and electrical insulation. After the war, the industry exploded into consumer products, medicine, and manufacturing. Today, silicone is so common we almost forget it is a triumph of chemical engineering, a material built atom by atom from one of the most abundant substances on the planet. The next time you stretch a silicone spatula, or feel the soft seal on a water bottle, or see a medical tube that saves a life, remember what you are holding. Not just a polymer, not just a clever invention. You are holding the result of sand, transformed by fire, rebuilt with precision chemistry, and engineered into one of the most useful materials ever created. If you enjoy stories that reveal how everyday materials are actually made, subscribe to Story Behind the Things